Good day to you all. I will be presenting my research on coal bottom as an anthropogenic soil to prevent soil erosion during post-mine rehabilitation in Sri Lanka. This is the content of today's presentation. Let's move to the introduction. Clay is the basic construction material used in manufacturing of clay bricks and roof tiles. About 64 million metric tons of clay was extracted in 2020. Many nations have formed rules and regulations for rehabilitation of mines. However, miners tend to abandon the mine due to the lack of suitable fill material and higher cost. As a result of this, many environmental problems tend to occur. As a solution for this issue, waste byproduct from different industries could be utilized as a backfill material. Coal bottom ash is an industrial byproduct of coal combustion process. Generation of bottom ash has moved to 730 million metric tons per annum, and from Lakvijaya power plant it is about 50,000 metric tons annually. Bottom ash cannot be used for any further activity in the power plant, hence disposed in open lands. This requires substantial amount of land. Therefore, power plant needs to spend a larger cost since it is a part of national regulation. Further, it has some adverse environmental effect. Therefore, disposal of this waste product warrants effective and eco-friendly mechanisms. Applications of bottom ash. Bottom ash is quite similar to sand, hence it has a great potential in geotechnical engineering. Bottom ash is utilized for many different purposes in various ways in different countries as shown in these diagrams. When bottom ash is used for mine rehabilitation, power plants able to provide the ample amount of material to fill the mines easily. This will reduce the cost of transportation as power plants and clay mines are located nearby in Sri Lanka. Further, this will move towards the conservation of natural resources. However, high precipitation in the tropical climate may cause soil erosion with a change in soil condition and leads to unsuccessful rehabilitation of mines. Therefore, evaluation of soil erosion in the post-mine land to which bottom ash is applied is important to verify the applicability of bottom ash. Therefore, main objective of this study is to investigate the potential of bottom ash against soil erosion. Methodology. For the present study, bottom ash was collected from Lakvijaya power plant and gravelly-lateric soil was used to prepare the mixed proportions. Initially, properties of bottom ash soil mixtures were checked out to find the suitability of bottom ash for mine rehabilitation. Then, soil loss was measured. Generally, universal soil loss equation has considered as a well-known technique. However, it has some drawbacks such as it is hard to find out some influential factors due to lack of guidelines, and the accuracy might be reduced as it developed based on the conditions of United States. On the other hand, soil erosion can be evaluated by artificial rainfall test. Further, it gives the measurement directly and has the flexibility of arranging different intensities. In addition, artificial rainfall test was used in literature to measure soil loss for fly ash and bottom ash mixtures successfully, and hence it was used in the present study as well. Artificial rainfall test. The figure shows the sample container and the schematic diagram. Sample container was made of PVC board. It is further divided into two parts by a board which contain percolation holes for infiltration. This facilitates to collect both surface runoff and infiltration water simultaneously and separately. This is a small video clip in artificial rainfall test. The rainfall intensities were set to 5, 10, 20 and 40 millimeter per hour. Precipitation was given for an hour continuously. The soil beds were refilled before every rainfall to regain the original conditions and overcome the soil loss from previous rainfall. The soil loss was calculated using the shown equation. Properties of bottom ash soil samples are presented here. Bottom ash exhibit low specific gravity, low dry density, high permeability, and high shear strength. Therefore, it is considered as a lightweight fill material which is suitable for soft ground like abandoned mines. Further, properties can be improved with the partial replacement of soil and can be recommended based on the field requirement. Microstructure of bottom ash and soil is presented. Bottom ash vascular nature is clearly from the SEM images, while soil has very fine pores. This behavior of bottom ash leads to low specific gravity, high permeability and higher water holding capacity. Annual soil loss. Risk assessment was categorized using Indonesian guidelines. Annual soil loss was decreased with increasing bottom ash content. It is maintained within the very low risk assessment class when the bottom ash fraction is more than 75%. Volume of surface water is decreasing with increasing bottom ash content, while it has an increase in percolation water. Therefore, fine content, permeability, and water holding capacity are the decisive parameters in the selection of bottom ash and its mixed proportion. Interestingly, the variation can be well represented with these parameters as shown in these graphs. According to fine content, sample should contain less than 20% to fall under very low risk assessment class. Likewise, permeability should be greater than 3 into 10 to the power minus 5 meter per second and water holding capacity should be greater than 55%. When comparing the results with literature, it clearly shows the influence of heterogeneity of bottom ash. Even though coefficient of permeability values are similar, despite the fine content, water holding capacity of Indonesian bottom ash is lesser than the Sri Lankan bottom ash. Now, I will be concluding my findings. Bottom ash has great potential to prevent soil erosion. Fraction of bottom ash should be more than 75% to fall under very low risk assessment class for the bottom ash used in this present study. Permeability, water holding capacity and fine content are the decisive parameters in the selection of bottom ash and its mixture. Variation of annual soil loss with the decisive parameters can be well represented. The following recommendations were made based on the present work. Bottom ash from different power plants should be investigated due to higher heterogeneity. Different types of material as partial replacement for bottom ash should be tested. Leachability of bottom ash should be investigated. Soil amendment capacity of bottom ash needs to be evaluated. Long-term effect on environment should be investigated. These are the references used in the present study. Thank you.